Good afternoon, everyone. I'm Youwei Liu, a PhD student from Syracuse University, working with Dr. Melissa Green. I'm going to talk about persistent homology of patterns generated by point vortex motion. Here is a simulation of 64 point vortices. There are 622 random assigned weak vortices, which are marked by red and blue dots, and 2 strong vortices marked by yellow and assigned dots. The red and yellow represent positive vortices, while blue and cyan represent negative vortices. Now looking at these clusters, we already know some basic information like the trajectory and the vorticity of these dynamic points. Then what else we could dig out from these point clouds? Like how these dynamic points interact with each other, and how can we describe this interaction, and what's the topological structure of these clusters, and is there any connections that could be built between the topological connectivity and the physical interaction. Topological data analysis refers to those statistical methods that find topological structure in data. Here I want to introduce a particular method called persistent homology. Persistent homology is a tool that measures the features of a topological space. Now let's take a look at this example. So as shown here, there are 23 data points located in a 2D plane, and we are only concerned on one property, for this case, the Euclidean distance between each data point. This means that we are evaluating the connectivity between each point based on their Euclidean distance. Then I need to introduce a parameter epsilon called the distance cutoff. As shown here, we could choose a random value for epsilon and using it as the diameter to draw a circle around each data point. As we increase the epsilon value, we could see that the circles start to overlap with each other. And here we see that the connections is created between these data points. As we keep increasing the epsilon, more points get connected to each other. As we said before, persistent homology records the topological features of data, and the Betti number is one way to count for specific structures. So different Betti number counts for different topological structures. And for example, for this one, with a very small epsilon value, there's no connections has been built. So the Betti 0 equals to 23, and each data point is individual. With a bigger epsilon, some points are connected, and we call this small cluster of connected points as one connected component. With a specific range of epsilon, we see that all data points are connected as one component, and there is a topological whole here has formed. So for this case, the Betti 1 goes to 1. And finally, as epsilon goes too large, all circles overlap with each other, and all data points get connected. So the Betti 1 go back to 0 again. In our example, we are using the Euclidean distance as the measurement of the connectivity, which is called distance function. The distance function is a key function that determines how the properties of the datasets are evaluated to build up the connection. And we store the distance information in the adjacency matrix. The mathematical expression for adjacency matrix is like this. And for example, for the A12, it represents the distance between point 1 and point 2. So for our case, the size of this matrix should be 23 times 23. Based on the definition of adjacency matrix, the distance between point I and j is always equal to the distance between point j and I. So it should always be symmetric, while the diagonals are always 0. And here is an image of adjacency matrix with scaled color for our example, as the yellow represent high distance value and the blue represent low distance value. Topological data analysis has been applied and developed in many areas. Here are some examples. So in Topaz's paper, they interpreted the persistent homology of several biological aggregation-inspired mathematical models by applying the Betty numbers. As shown here, so figure 1 is one example of the simulation, and obviously for all the simulations, the change of the topological structure along the time sequence is also a very important behavior that need to be captured. So in this paper, they also proposed a new visualization method of Betty number called Crocker plot. And here's the example of the Betty zero Crocker plot. And I will introduce this method later. In Taylor's work, they proposed a mathematical toolset based on network structure analysis and apply it on two-dimensional decaying isentropic turbulence flow. So in figure 1 here, it shows how the stress of the vertical interaction between the elements I and j is quantified through the vortices and the induced velocity, respectively. And in the figure 2, it shows the results of the scale-free network of the vertical interaction in two-dimensional turbulence. As the last example in Kruger's work, they applied the Gabriel graph theory on quantitative classification and comparison of periodic vertical flow pattern. And in this figure, it shows an example of matching the two flow fields, which are both reverse von Karman vortex streets. And we can see that the critical points and the graph edges are classified and compared for the two flow fields. And all the solid lines indicate the matched critical points, and the dashed lines indicate the graph edges. Okay, now let's take a look back at our simulation here with a sense of the trajectory range in the 2D axis. As you can see that the points moving around with a possible maximum Euclidean distance equals to 40, and the magnitude of the two strong vertices are approximately 10 times of those weak vertices. Also, the origin is marked in this movie. The traditional way of visualize Betty number results is barcode, while the shortcoming of this method is that it cannot present the results in regard of epsilon and time sequence at the same time. So here we introduce the Crocker plot, which is proposed by Topaz, as we mentioned before. Here as an example, the simulation results using Euclidean distance as adjacency matrix are plotted here under Crocker style. So the left one is the plot for beta 0, which represents the number of clusters, and on the right is the plot for beta 1, which represents the number of loops. Like we said before, the Crocker plots track the beta number across both proximity scales and simulation times. So how do we read the Crocker plot? Since the x-axis represents time sequence, the vertical slice here corresponds to persistent homology analysis of one single snapshot. And then we can read the values of beta 0 and beta 1 corresponding to the different distance cutoff. Similarly, horizontal slice tells us how many clusters and loops are formed over time at a specific scale. And moving level sets indicate that natural separation scales change over time, while the large patches indicate that the topological features are persistent across scale and time. So these are the advantages of Crocker plot, that we could observe the persistence in a 2D way. So for our simulation, 3 different distance functions are tested. The equations are shown as below. So the first equation evaluates the properties as a 3D-like normalized distance. As you can see from the equations, the vorticity is supplemented as one dimension. This means that the 2 points need to reach 2 conditions to stay connected. First, they need to be both close in locations, and then they need to be similar in vorticity value. For example, as shown in this diagram, we could say that the two blue dots are connected since they have the same vorticity and the Euclidean distance r is very small here. While if we take a look at this red and blue dot here, though they are having the same small r, but they are having contrast vorticity value. So this term could be much bigger, and we could not say that they are connected at this point. On the contrast, if we take a look at these 2 points, while the red dot here has a very small vorticity value, so this term in this case might go smaller. So we could say that these 2 points might be connected to each other at this point. For this equation, it evaluates the induced velocity of 2 points as the adjacency matrix. At this point, we said that 2 points are connected if they are close and the induced velocity of each other are strong. Again, we use a simple diagram here to explain this. For a flow field like this, we have 2 dominant vertices and some weak vertices surrounded. This one rotates this way, and this one rotates this way. Under this criterion, 2 points could be connected when they're close on location, and also at least one of their induced velocities is large on each other. For instance, for the 2 strong vertices, they are connected with these weak vertices around them, but they are not connected to the points far from them, like this one. Of course, points with similar vorticity value but far apart from each other will not be considered as connected to each other. This equation is come up from the impulse theory. The impulse theory is trying to get the theoretical prediction of total force and moment from arbitrary motion and deformation in a flow field. We get this equation by simplifying the impulse theory equations for our point vortex case. But the general idea is shown as in this diagram. The forces generated by vortices on a chosen point could be calculated from the flow field, and we define that 2 points are connected if their induced forces on a chosen point are similar. In this diagram, it's supposed to be able to divide the leading edge vortex and the trailing edge vortex by evaluating the forces they generated on the quarter point of the airfoil. Here are some results of this equation. As we can see from this plot, number of clusters in this area is persistently equals to 3 over threshold and time. And here we take a snapshot from this area. We can see that the data points are divided into 3 components as indicated by the beta 0 plot. There are 3 different shapes representing the 3 clusters. We can tell that the 2 strong vertices are captured and identified as 2 components, while for the rest of those weak vertices, they are all connected at this moment with specific distance cutoff. And for plots of the number of loops, length scale in area like this, the loops form and remain constant through the simulation indicates that the points mostly rearrange but not drift apart. For this inverse bias law equation, we could observe the persistence for number of clusters like here over time and length scale. And similarly, on the corner is a snapshot for selected length scale and time frame. For this case, the number of loops grows dramatically fast from 0 and goes back to 0 only at the large threshold. And like At area like this, number of loops shift around even after every component connected, as indicated by the number of clusters. For this impulse-based equation, we observe 2 and 3 clusters persistent over shorter patches of threshold length scale and time. From the top right figures here, we can see that the 3 clusters are the 2 strong vertices separately and all the weak vertices collectively. This shows that the matrix picks out the features that has distinct effect on the point of interest. Smaller and weaker vertex cluster could potentially be identified as negligible. For this figure here, the number of loops stays low. This means the loops are barely formed in this case. So for the current work now, we could say that the persistent homology do provide us a new way of quantifying the flow field structural and behavioral patterns. And the several distance functions are tested and reveal the connections between vertices. For the future work, we are expecting to integrate FDLE features as knots to design and calculate adjacency matrix. Also, we are expecting to establish characteristic Crocker patterns for common vortex structures and phenomena. And here's the reference for this presentation, and thanks for your attention.